The microscope is an optical instrument used to view objects of very small sizes. The apparent size of the object viewed through the microscope is many times larger than its actual size. Primarily, the apparent size of an object is determined by the size of its image on the retina, which in turn depends on the angle subtended by the object at the eye. When the object is far from the eye, it subtends a small angle at the eye, and hence its apparent size is also small. As it is moved closer to the eye, the angle subtended by it at the eye increases, resulting in the increase of its apparent size. We know that the closest distance for comfortable view is the least distance of distinct vision, or the near point, usually represented by D. When the object is placed at the near point, the angle subtended by it at the eye and its apparent size is the greatest. If the object is closer to the eye than the near point, the eye cannot focus its sharp image on the retina. But a simple microscope or magnifier can be used to view such objects without any strain on the eye. A simple microscope is a converging lens of a small focal length. If it is placed between the eye and the object such that the object distance u is less than its focal length, then the erected magnified virtual image of the object is formed beyond the near point. The angular magnification, or the magnifying power of a simple microscope, is the ratio of the angle subtended by the image at the eye when seen through the microscope to the angle subtended by the object at the unaided eye when it is placed at the near point. If theta is the angle subtended by the image at the eye when the object is seen through the simple microscope, and theta naught is the angle subtended by the object at the eye when placed at the near point, then the angular magnification, or the magnifying power m, is equal to theta by theta naught. Now, let us find some useful expressions for the magnification of a simple microscope. If the height of the object is h, then tan theta naught is equal to h by d. But for small angles, tan theta naught is approximately equal to theta naught. Hence, we can write that theta naught is equal to h by d. Let this be equation 1. When the object is viewed through a simple microscope, the angle subtended by the image is the maximum when it is formed at the near point, and minimum when it is formed at infinity. When a simple microscope is adjusted in such a way that the object is at a distance slightly less than the focal length of the lens, then the virtual image is formed almost at infinity. This situation is known as normal adjustment. When the simple microscope is set for normal adjustment, and the angle subtended by the image at the eye is theta 1, then tan theta 1 is equal to h by f, or theta 1 is equal to h by f. Let this be equation 2. If the angular magnification of the simple microscope when the image is formed at infinity is mi, then mi is equal to theta 1 by theta naught. On substituting the values of theta naught and theta 1 from equations 1 and 2. And on further simplification, we get the angular magnification or the magnifying power of the simple microscope as mi is equal to d by f. Let this be equation 3. Now let us find the angular magnification of the simple microscope when the image is formed at the near point. Let the angle subtended at the eye by the image when formed at the near point be theta 2. From the ray diagram, we can write that theta 2 is equal to h by u0. Let this be equation 4. If mn is the angular magnification of the simple microscope when the image is formed at the near point, then mn is equal to theta 2 by theta naught. On substituting the values of theta 2 and theta naught from equations 4 and 1, and on further simplification, we get mn is equal to d by u0. Let this be equation 5. But from the lens formula, we have 1 by u is equal to 1 by v minus 1 by f. Using the Cartesian sign convention, we can write that u is equal to minus u0, v is equal to minus d. Substituting these values in the lens formula and then multiplying both sides with minus d. And on further simplification, we get d by u0 is equal to 1 plus d by f. On comparing this with equation 5, we get mn is equal to 1 plus d by f. Let this be equation 6. From equations 3 and 6, we observe that the magnifying power of the simple microscope is greater when the image is formed at the near point than when it is formed at far point. We prefer to have the final image formed at the far point because the images formed at the far point can be seen by a relaxed eye with minimum strain. When greater magnification is required to view microscopically smaller objects, a compound microscope is used. A compound microscope consists of two convex lenses arranged coaxially. The lens O that is close to the object to be viewed is called the objective, and the lens E that is close to the eye is called the eyepiece. The objective of a compound microscope is of a small focal length and has a small aperture, whereas the aperture of its eyepiece is large. Let a small object AB be placed at a distance that is just greater than the focal length of the objective FO. When the light rays from the object are incident on the objective forms an image A'(B'), which is real, inverted, and magnified. This image A'(B') acts as the object for the eyepiece. If the position of the eyepiece E is so adjusted that A'(B') lies between the optical center and the first principal focus, then a virtual and magnified final image A'(B') is formed. Let the height of the object AB be h and the height of the image A'(B') formed by the objective be h'. Let us also define the tube length L of a compound microscope as the distance between the second focal point of the objective and the first focal point of the eyepiece. If MO is the magnification due to the objective and theta is the angle that the ray refracted by the objective makes with the principal axis, then MO is equal to H dash by H and tan theta is equal to